Mhm. Today, okay. First of all, yeah, thank you to be here again for the course entitled Think Mathematically, Act Algorithmically, and subtitle Optimization Techniques. Just a few words about a possible structure of the course. As I told you before, as I told you before, the course is organized, is topic organized. This means we will consider here, let me say, some topics, and they are connected by the common denominator optimization techniques. We will start today with the application of least square method in order to, as I put here in a comment, no, for a soft start, but not only for a soft start. Soft means, I think, you know a little bit. We will see that you have seen this method or the methods in some different courses. This means for a soft start. The other reason is I need to recall some concept, or I need this basic knowledge in order to go ahead with the rest of the course. We will see particle swarm optimization methods. I don't know if you heard about that. It doesn't matter. No, in complementary study, it doesn't matter if you didn't hear about anything. The reason is the reason is rooted in the word complementary. No? If you already know, you don't complement in this sense. Therefore, it's a course for everybody. I try to really to use to repeat many times concept. I try to use in an easy yeah, language in order to be comprehensible for everybody. Let me see. Mm. Um, we will see after starting in the soft way with the least square, we will see together this particle swarm optimization method together in the sense. Yeah, please, please.
I'm sorry for that. The your podcast is just latex.
Okay, I didn't share. Yeah, I didn't share. If I don't share, please inform me because sometimes I am happy to work in another university. I am a guest professor, visiting professor at the University of Łódź in Poland, and there we use Teams. In Teams, I can share directly the screen, and then I am happy to hit these Teams. Sometimes I forget to share. Thank you, thank you. Because in Zoom we have this problem that each time that I change window, I have to share again. It could happen that I forget. Thank you. Uh, when I say we will do together, I would like to intend that I will try to introduce also or to show you some applications using MATLAB Simulink. Therefore, I use the word together. I mean, in order to emphasize that we will try to do some application again together. Just to understand a few things, and then I will come back during the semester. We will see that also after these two chapters, so that these two first topics, least square and particle swarm optimization method, we already have an idea about what is an optimization problem, definitively. Also today we will start. But not only what is a convex optimization problem, as a non-convex optimization problem. We will see. Also today about the definition is not a problem to speak about definition, but to work with them is something more to learn the definition. It's always so, no? To really to apply, to act algorithmically, in my opinion, is more difficult than to think mathematically, even though we cannot act algorithmically if we are not able to think mathematically. But in my opinion, and this is also the goal of the course. Very often, probably I am thinking so because I am an engineer, to apply help also the theoretical part. I mean, of course, without theory, we cannot apply. But the application allows to validate, allow to understand better the theory. Therefore, I will try also to show you something with MATLAB Simulink. Of course, we don't have much time. Therefore, I would like to say, and I will tell you a little bit next time during the semester in what consists of what consists the examination. The examination is a project. Through the project, we can go in depth, more in depth on these topics, or topics also which I didn't consider here. But in any case, topic related to optimizations. Because these selected topics, in my opinion, are topics which allow us to really to understand what is an optimization problem is, what in convex, not convex optimization problem are. And I introduced some techniques, and these techniques is the basic techniques, or in general, once we understood one of the two techniques, then we are able to generate, to work also with techniques, even though we didn't consider in the course. This means the project could also done with the techniques which I didn't tell you. If you have, for instance, a particular problem which we want to attack with the knowledge of optimization problem, or optimization, it could be that your problem should be attacked with a technique which we didn't consider here. But speaking with me, I can suggest which one, and we will see together that the optimization techniques really, even though they are different, they are related together because the main concepts very often are the same. Then we will go ahead with the application of recursive least squares method in identification. Again, identification, I don't know if I told you, identification is optimization. This we will see also today. Then, very important, some elements of model predictive control. As I told you, I am here responsible for control. Of course, at least one techniques related to control should be done. And this is one of the most important, I don't want to say so probably directly, but one of the most used. We will see here just basic knowledge, basic knowledge. Then we will see trajectory optimization with dynamic constraints. This is also a nice topic, related also to model predictive control, if you want. We will see a little bit something related to Lagrange method. Because sometimes I had here in the course students who belong to economic courses, and this is also very often applied. I will tell you very quickly about the Newton and Raphson Newton numerical methods, because very often the problems not only in term in everywhere, I would like to say in every methods, they are not analytically solved or solvable. And then in this sense, we have to use really numerical approximation. I will tell you a few words exactly in a few minutes. This means I will flesh out some idea, but working with the computer, we will see a little bit something also in this direction. About the appendix, I am not sure if we have time to do really in depth something related with the Hamiltonian function. In fact, it is written eventually. The Hamiltonian function, or in general, Hamiltonian methods are optimization methods which can be applied, but eventually we can do together in the project. I don't know if we have time, therefore I put here as an appendix. Let me start in just two slides, the slide number 3 and the slide number 4, or number 4 is just an introduction, just to put some possible definition. Let me see. Classification more than definition. Convex optimization. Do you remember at the beginning I told you I classify the problem in two categories: convex optimization problems and non-convex optimization problems. If I am able now to define what a convex optimization problem is, we see that directly we can understand what is non-convex optimization problem is. We can see from this possible, let me see, definition is not exactly the right word because it's not written definition in the sense. I would like to tell you in this sense, the convex optimization problem or the convex optimization is a subfield of mathematical optimization that try to minimize convex function over convex sets. From this sentence, or for this explanation, it's a little bit difficult to understand what they are, this convex optimization problem. But fix, for instance, a convex function. This is easy to from high school. Something that convex, concave, probably you remember this. We have also, I don't have here, but also I can look at the definition, mathematical definition. Do you remember? If the segment is always in the upper part of the curve, I can write also the mathematical definition. But it's intuitive, what is x up to 2 is a convex function. Of course, x up to 2 is a convex function for each x. But if you consider a polynomial, in fact, at the end, we have a polynomial time algorithm, even though this is related to a different problem. But if you consider a polynomial function, a general polynomial function, we can speak about a local convexity and local not convexity, because if you have many valley, let me say, many hills, of course, we can consider that not everywhere that we have in a segment that is always up with respect to the function. Intuitively, I already explained what a convex function is. And of course, in a convex optimization problem is a little bit more complicated, but needs a convex function. And then we can see that needs a convex set. About that, we will see a little bit together the meaning during the semester. But if you don't have one of these two, let me say, conditions, we are speaking about non-convex optimization problem. More practically, to sum up, we will see that in a convex optimization problem, admit always just one solution. Could be a maximum, could be a minimum. When we think about convex, we are related to a convex function. We think about x squared, the segment is in the upper part of the curve. When we speak about convex optimization problem, the problem could be also convex, in the sense that the definition, or this practical definition is more effective, even though the function is not convex, but you have just one solution. I mean, x squared is a convex function, right? Minus squared is a concave function. One has one minimum, one is a maximum. When we speak about problems, we don't distinguish between min and max. I will tell you why. I can tell you immediately why. We don't distinguish because an optimization problem could be formulated in terms of mean, an equivalent form in terms of max. Example. And at this moment, I have in mind just a technical example. But an economic example is I have a production system. I can, from this production system, minimize the cost. But in the meantime, in the equivalent form, I can maximize the profit. Something like that. I'm not expert in economics. And in technical fields, I worked a lot, for instance, in electrical drive, in electrical machines, in which we try to find the structure of a machine with the maximal force or the torque, generated torque, with the minimal volume, with the minimal weight. Very compact machine, very strong, roughly speaking. This means the cost function to be minimized, to be maximized, is force divided volume or the weight. Very, very small machine, but very strong. I try to maximize the force with respect to the volume, to the dimensions. Very, very small machine, very strong. With respect to what? With respect to dimension of the rotor, with respect to number of coils, to maximize the force with respect to the dimension. With respect means x squared as the minimum with respect to x. I minimize to find the minimum of x squared, x equals 0. The derivative in high school, you remember? The maximum of minus x squared is again 0. In this case, the example of the duality is not correct. Because I have to consider 1 divided square, but 1 divided square is in a function a little bit strange because in 0 is not defined. But in the meantime, if you think about my example, force divided dimension, I try to maximize with respect to what dimension of the rotor, a number of the coil, is equivalent to minimize dimension with respect to F, force. Of course, I need to parameterize the force of the motor with respect to number of coil, dimension of the rotor, and so on. I don't know, for engineers, it's not so very easy to understand what I intend, but to sum up, a minimum, to find the minimum is the equivalent in terms of optimization problem to find the maximum. If you consider 1 divided the cost function. Just to flesh out about convex optimization problems and so on. We will come back during the semester many times for using different examples and so on. To conclude, and then we will start with the lecture of today, but this is also a part of the lecture. We will see together not only convex optimization problems, not convex optimization problems, and so on. Particle swarm optimization methods are dedicated to not convex optimization problems. We will do together again with MATLAB symbol. Another important classification, not only convex and not convex optimization problem, I try to explain intuitively, is related to the methods which we are using to find the optimization element which we need in our problem. The optimal element, optimal elements through optimization methods. And these methods are classified in direct and indirect methods. Let me read the last sentence and then we will start with the technical lecture. An indirect method works by analytically constructing the necessary and sufficient conditions for optimality, which are then solved numerically. A direct method attempts a direct numerical solution by constructing a sequence of continually improving approximation to optimal solution. It seems to be really confused. I copied from a book. I try to clarify in the context the meaning of the word direct, and then the word indirect. In this is the language related to the optimization method. Look why I will start with direct. I copy from a book. I don't know if I put the lecture to here. I know we will see. We will see later. This direct method is connected with a numerical solution. This means I try directly to attack the problem numerically. This means the numerical method or the numerical way to solve an optimization method is the more natural way to do. The reason is the most of the majority, I would like to say, of the optimization problems are not convex. In the presence of not convex optimization problems, typically we don't have the possibility to solve, look here, analytically the solution. We speak about indirect method if I am able to attack the problem analytically. This is a little bit the language which we will use, but very important to remember that we have a direct method, which is a numerical method, and an indirect method, which use analytical formulation or the use conditions for optimality, and then this is important now, we clarify with this sense, solve numerically. Therefore, we speak about indirect. Of course, it could be, we will see exactly now with the method of least squared, the first method of least squared, that the indirect method does not need to use a numerical procedure. Of course, we use nevertheless a computer, but just for the calculations. It's a little bit confused now, but I will show you that we have an analytical solution. This is the solution, one solution. Could be also more than one. In this case, the problem is not convex, but it's not so typical to find really analytical solution if the problem is not convex, but it could be. This is already the solution or solutions. But of course, practically, then I have to calculate the solution. In this sense, we are not speaking about numerical solution. Numerical, if you have approximations, if you have a method to approximate, to calculate. In this case, it's just a calculation. If I write 1 + 1 = 2, this is a calculation. It's not a numerical method. It's, of course, I use numbers. But if with the language numerically solved numerically, it means that we have an iterative method. Again, direct method, I will use this iterative method to find the solutions. It's the most important, but it's used, the most used. We will see in particular with particle swarm optimization methods. We speak in our context about solvers. I don't know if you heard about that. What is a solver? And a solver is a method, is a tool, more general, is a tool which allow to calculate numerically the solution of the problem, in our case, in an optimization problem, directly, numerically, with steps, calculation. The word iteration is no problem, but we will see together. Indirect means I can consider some conditions, mathematical condition. We can see necessary and sufficient conditions means also theorem to find an analytical solution. And then, of course, I need to calculate, but I don't need numerical steps to approximate. Probably this could be a key word to understand, to approximate or to calculate in approximately way the solution. Okay, let me now pause. I uploaded this material and the lecture now in my study, and then we will go ahead with the first topic, least square. So if you want download, you can do for this presentation. Of course, you don't need because it's all just was an introduction on the course and the keywords, direct, indirect, convex, not convex, and so on, optimization problem. Let me go in my study if I am able to do. Okay. We take 2 minutes pause. Oh, what I'm doing here now? New thing? Okay. Let me go to the course. Okay, here. Material, let me share so you can see what I'm doing. Right. Okay, I would like to, here we are inside, no? Yeah, correctly. Let me generate, I would like to write today lecture number 1, or the date probably is better, no? I don't know. The date of today, no? 0804, right? So it's okay, no? Very important that the material is there. And this is okay, I would like to upload 2 presentations now. I will use also, let's see here. I have in a couple folders. No? I will use some material and also presentation. Sometime I will write with my hands as an exercise. Anyway, this is therefore I have the camera here. No? Okay, let me see. Now I forgot what. Okay, I have to upload. Tutorial we don't need. How many students we have here in data science? Just what? For you, probably you already seen some optimization methods. Some, okay. In fact, you can see that also for you, if you look at the list of possible topics, I will do, I think I will do everything. The appendix, I'm not sure, the appendix. Um, should be also for you something in complementary, because for instance, control, I don't think so that you did model predictive control. PSO, you did? You know already. Okay, for you, it's just a repetition as today the least square. But anyway, I hope that also for you something should be complementary in this sense. About the project, we will, or the examination, we will tell you probably also next week. Uh, but it basically is ad personam, we say in Latin. This means depend of your background. Huh? In your case, we will see what could be complementary for you. If you are students in economics, we will look at what could be useful for you. This is the method to formulate a project and then to do examinations. It's in a personal, let me say personal in the sense, is oriented to the background. Therefore, is also acceptable if you are already in the project. But of course, in the context of optimization, in which we apply the method, not necessarily one of them, but an optimization method. Because we will see that the optimization methods, I don't want to say they have similar way or the similar tools, but they have a common denominator in the sense. Okay, let me go ahead now. Here, what I'm doing now. Okay, here. Okay, introduction is here. Okay, this presentation is already there. Let me upload another one, and then we will restart with some technical issues. I think it's this one. I hope it's the. I'm not sure if this is the last version, but if it's not, I will re-upload later. But the difference is they really. It could be that you have some small changes, some improvement. Okay, let me open. Uh, Also here I have the problem too. Let me compile again. Oh, ah, this was before. Let me close. 1 second. I do this. It could be that I need to open the file with LaTeX again. I don't know why.
I can see the slides from my study. Yeah, I can open them. That's the session one.
Yeah, why I don't see it?
I don't, I don't know. That's the
Strange, no?
second one. It's the introduction. Just.
But it's strange. Now, for me, it's impossible to understand what happens. Really, uh, let me try again. I'm not able to close what I would like to close. I'm not able to see what I would like to see. Let me try again. Ah, no. There is something strange now, totally strange. Ah, okay, here. This was, no? No, it is. seems to me doesn't work. Okay, let me compile again. Okay, this is the file. Okay, now I see. I would like to restart with the to record, but I don't see now the possibility. Did you see something here? For probably here.
Yeah.
Should restart, yeah? Yeah, I think we are recording, yeah.
Yeah.
Okay, let me share now. As I told you, Teams, the sense is easy to be used. Okay. Okay, let me start now with this method here. Before speaking about the least squares, let me introduce a little bit some fundamentals, some background. Direct, indirect, we will see in a few minutes again. But let me start with the word simulation. Simulation is an imitation, we can see here, of the operation, or in general, operations of a real world process, of course, but in general, we say about a system or systems. But of course, real world reflects a little bit more, let me say, the possibility to apply. But in general, a system is something more abstract in a sense. Over time is important because you remember at the beginning I told you we are working with dynamical systems. Dynamical system means, or at least our final goal, means that something change over time. And not only, we will see that the dynamical system is connected with changing the changes, which is defined over time. Our functions are defined over time, but we have a feedback. We will see what I intend. To simulate, we need a model. We will see that the keywords, the important keywords, is characterized or they are written in a red color. What is the model? Yeah, now I try to explain really roughly because we have also mathematical definitions of these concepts, but I would like to go ahead quickly using just the intuitive idea. Is a model is a simplified and idealized understanding of the system, of systems, better to say. A system is more general, a real world eventually process. But if you system also, we have a mathematical definition. Real world process or real world, it's more intuitive probably, we can understand. If you don't like system at this moment, at this step, we will see system a little bit better later. Think about a real world. We try to simplify. I will be more precise. Question, very important question. Does a correct model exist? Now, if the word being correct means true, the answer is no. Does not exist a model which can be considered correct. But if correct means valid, then the answer is yes. Valid is related with this concept here, or this concept simplified and idealized. Sometimes in some books, we consider just simplified because and the idealization isn't a simplification. We are speaking about validation, and in general, we are not speaking about verification in this sense, because verification is related to the truth. Validation is related to something which can be used, can explain what you want to explain, can be used in an optimal an optimization problem, inside an optimization problem. This course is more dedicated to the descriptive statistics. I think I will not use, or we will see, no, we will see, and no concept related to the probabilistic statistic. And in any case, in this part here, definitively we will use almost just descriptive statistic, or just a few things about the probabilistic statistic. And the descriptive statistic is basically used to solve the non-parametric, or to generate, let me say, not parametric models. We can see the last sentence. In any case, we will not speak about the probability theory, just a few mean values, of course. We will see variance, we will see also in this course, but not in, we will not will consider in this course, in this part of the course. I will not consider explicitly distributions, just a little bit. In the next semester, in the Kalman filter, we will see that the probabilistic nature of the course is sure, I would like to say, stronger. No? We speak very important, nevertheless. Look at this red wording, non-parametric model. We will see today a non-parametric model. Even though the paradox is we will use parameters, but we're speaking about non-parametric model because the model which I will present now is the model which will serve for parametric model. I mean, when we speak about parametric model, we intend the differential equations, which consist of some parameters with physical meaning. Here, we will see that the physical meaning is not present in all parameters, but just in some of them. Let me do an example in order to understand what is a non-parametric model. We have a model, we need a model, but the classification is parametric, and the other class is non-parametric model. Very often, the non-parametric model is also inside the parametric model. Let me do this example, will be clear. Sometimes the nomenclature or the classification is not clear. And I mean, we have to be habitual with this, with the wording or with the concept, but it's not important to know that. It's important to know that exists, and then it's important to be able to use. But of course, in the course, I have to tell you about the literature, what they intend with some wordings. I will introduce now the least square method. No recursive case. If you remember in the list, I told you that I will consider also a recursive method. Iterations. Look at this, least squares method. It's very important to start with this method here, because no optimization course without this method, even though I will tell you very quickly. I mean, it's important nevertheless to tell you. Is always present, almost always present in each application. Probably not directly this no recursive case, but the recursive case very, very often. But the recursive case is based on this. Look at this picture here. It's written in German, but we have some points, measured points, classified by the variable x. We have x equal 1, y, which is violet here, equals, I don't know, 38, almost 40. Here for x equal 2, we have I don't know, I'm going to 2, the 3, it doesn't matter what. Here for x equal 3, we have 37. I don't know, for x equal 4, almost 80, and so on. We have how many points or how many measurements we have? Let me see. 1, 2, 3, 4, 5, 6, 7, 8. It's in a real system, in a real measurement, yeah. It's X represent the current, excuse me for this example in the engineer, and the Y represents the flux in the model. I am an engineer, you have to consider this. Question, we learned this in our school, probably in the school a little bit. What is the blue line which minimize? When we say minimize, we have to understand what? No? The distance between the violet points, or the points, no? And the blue profile, or the function blue itself. This blue function we called y hat. We have y measurements. It's not written, it's a shame. But anyway, this is y1, this is y2, this is, no, it's written, I see now. This is y in general. No? And y hat is the model curve, it's written in German. Is the model which minimize something. I didn't tell you what. I didn't tell you what. Because once I define what I have to minimize, change the curve. In the school, what we learn in the school? We learned that, well, in a possible solution of this fitting problem, the name is fitting problem, to find the curve, and the model curve is the model, non-parametric model. I will insist again later why non-parametric model. Which minimize something, I didn't tell you what, which minimize the distance, let me say, between, but something in a sense, and the distance is something, but depends how we define this distance. I mean, in the school, we learned that, why not? I can consider a curve we pass through all possible points. It seems to be a possible solution. It is. Instead of this, let me say, line, this blue line does not meet any violet points, right? Why should it be the best? Yeah, this is the possible question, which I will now answer directly, defining something to be minimized. Typically, it's in the distance. But believe me, the distance could be defined in different form. Now, look at the end of the slide. You have a possible mathematical model. Here should be better if I write possible mathematical model, but I tell you. This mathematical model, the possible mathematical model in this is, today we will consider also a different mathematical model, is in a polynomial structure. We will see a trigonometric function, we will see next week, I hope. At least I would like to show you two possible mathematical models, polynomial and trigonometric typically, but we can consider also exponential. We can consider also any kind of basis. I don't want to go in depth in mathematical aspects here, but of course, this is a possible mathematical model which reflects or will represent the blue line. Assuming that this is our choice. Also, this could be discussed. Is the best one, is the optimal one? We will see next time a little bit better. Assuming that is the model of the mathematical model which I want to use today in order to determine the blue line. I mean, I give you this example. Try to calculate the best polynomial, the best blue line in form of polynomial, Could be again in form of exponential function, in form of trigonometric function. This we will see later. Which fits in the best way the points, the measurements, these violet points. Why? The white points. Of course, when I say so, I didn't define the problem because the problem is fully defined when I define what I have to minimize, the distance, for instance. No? But to define the distance, it's also something not unique. We can define different distances. Let me go ahead. The problem is that typically we have two kinds of errors, a statistical error and a deterministic one. Or at least we can think about two kinds of errors. Basically, deterministic, it's something related to the model. The polynomial is a deterministic structure. And statistically, something related to the, let me say, measurement itself. We will see in a few minutes. This last part of the slides is related at the choice of a possible model. We will see also, it's called also basis, polynomial, trigonometry, and so on. Is of course related to deterministic error. In our case, once we have if I choose to work with the polynomial, yeah, the problem becomes to calculate the order of the polynomial, which is related to the number of coefficients. I don't know, we can see here. No? The number of coefficients is n plus 1, in which n is the order of the polynomial. This problem here is quite complex. We will see, I think, next week or after next week, a little bit more in depth. But in any case, we can see that different elements play in a role in this problem. But this first sentences, this part here, is of course related to the deterministic aspect, because the deterministic is something which I know. The structure of the polynomial, this means the order, or which kind of basis, trigonometry, exponential, polynomial, and so on. Of course, this generates also an error, always, because I can choose a different regressors, we say in this concept, different bases, different functions. But different functions, different errors, deterministic errors. The statistic is related to the measurement. I measure 1, I measure -1. It could be that the true is 0. No? Statistically, let me say, just roughly interpreting the words. We can consider two kinds of errors. The last sentence is the key points of today. I will conclude. Do you have a little bit time, or do you have a lecture? Because my idea, I start a little bit later, but I would like to 10 minutes. Do you have 10 minutes for me? I would like to introduce the cost function because it's the key point of this part here, and then next week we will see that will be a little bit more. But I would like to tell you until here in 10 minutes. It's not much. In order to solve really the problem at the end, to obtain the blue curve, we need to define a cost function. Is a cost function, or in some books we can see figure of merit, or the figure of merits in general. No, as I told you, we can define many different figure of merit, many different cost functions, and therefore we use often the plural to attack the problem. Without this, we cannot really solve the problem, at least in the context of an optimization. We need the function to be optimized, to be, in this sense, minimized, because you remember I told you, and a possible definition is to find the blue line which fits in the best way, assuming the minimal distance, in the sense I have to define a distance and a cost function, to obtain the structure of this blue line. At the end also to draw, to graph this. Let me show you the example. In your opinion, here we have 2 points, left and right graphs. You have 2 points, 2 measurements. With an instrumentation, I have 2 measurements. And I have 2 possible approximations if I am considering a polynomial which consider a constant and which consider an line. Basically, here we have an line which is characterized by, let me say, a0x plus a1. Here is characterized by a polynomial a1. Basically, n equal 1, order 1, n equal 0, polynomial order 0. If I ask you, what do you think? This is better, the first approximation and the deterministic approach, let me say deterministic approach, or the second approximation, a statistical approach? And I will clarify why in some books they use this wording, deterministic approach, statistical approach. Your opinion, do you have an idea what is the best?
I think the statistical approach is easier to be applied because there are lots of variables to determine exact number to obtain some formula. In this case, I can say the statistical approach.
Because in your opinion, it's easy to be calculated. That is the criterion, of course. The meaning is I have to calculate just one parameter. It's in the criteria. If the criteria is to minimize the number of parameters, definitively. I formulate in a different way, but anyway, I accept also this possible cost function, the minimal number of parameters. I formulate in the sense, what is the best fitting? This means I allowed also to consider more than one parameter. The best answer is always, it depends. You were already in master, no? When the professor say, what is the best? Better say, it depends. No, this is, you can also manage that. But the answer is good. The answer is good because nevertheless, both is possible solution. Your answer didn't answer directly my question because I fixed also not properly, but indirectly, not properly because properly means in our fields in optimization to write a function mathematically. When I say fit, it's unclear. What is fit? It is fit or is this fit? It seems to be that really fit better. I meet both. This means this fit. This not to fit. Really, excuse me if I play with the words. This meets both. This fit. But this also fit. Meet is, I mean, we will see now what I intend. The best answer, it depends. I will clarify why. But your answer is good. Because your answer say both fits. This use less calculation. Okay. I was not clear why your answer is good. It's not clear if this fitting is better than this one, because I didn't define mathematically, quantitatively, just with the wording, just qualitatively. If I speak about fitting, if I speak about meeting, to meet just qualitatively, it's in the wording. In optimization, we need to quantify. Missy, go ahead. Few minutes, and then next week I will try. I will tell until here. It could be that is not the last. But we upload I see something should be improved, but just a few things. Look at this. Before introducing the cost function, which must be minimized, and a norm and a distance. Here, when I speak about fit, it's unclear what is fit. This isn't a fit. I meet, this means fit. Here's a fit. I don't meet, but it's fit. It's just qualitatively. We are meeting qualitatively, we are not able to answer what is the best. Therefore, I told the answer is depends. Let me, a few minutes, introduce these mathematical aspects, and next week, really very boring lectures with mathematical aspects, and I try to introduce also MATLAB. Do you know MATLAB a little bit? You know, okay. But not everybody, no? Not everybody. Look at this expression here. What I am doing here. Here is exactly our model. Hat is the model, no? Approximation. Hat is always in our notation, the approximation, the model. The model is always, do you remember? Simplification, idealization, approximation. We can say approximation. What I'm doing here. Y1, Y2, Ym are our measurements, real value, tuck, tuck, with the instruments. Is the true? It's not the true. The measurement is not the true. Very important to understand. Does not exist. At the end, if I want to say in an extreme sentence, the data does not exist. Exists just their interpretation. I have some data, but they're not the reality. They reflect something of the reality. I will clarify next week a little bit better, but you can understand that we have errors. We have a systematic error, statistical error. This means reflect something that happens, reflect our phenomenon, but it's not our phenomenon. Reflects. This means it's not the truth. Therefore, at the beginning, I told you our model is not a real true model. It's valid. Let me go ahead. Y1 is circa this expression here, in which I try to calculate my polynomial at point x1. In Gymnasium, you did this. It's exactly here. This point here is y hat calculated at x1. This x, current in our case, the name of x is exploration variable. I explore the phenomenon. I mean, I put in the model in a current 1 ampere, and I measure more or less 40 Weber flux, something like that. And x1 is this here, x1 which I measured. x1 hat, which is, excuse me, y1, which I measured this one, y1 hat is here. We see the difference between y1 or y hat 1 is y calculated x1 in accordance with our model, with which we want to describe our phenomenon, which is related to these measurements. I do this calculation for each point. We have 2, 4, 5, 8 points, I told you before. And I have these expressions here, which we can see that the measurements are approximated. Could be also, I can meet also, but we will see that meet is not the best way to proceed. I will tell you in a few minutes, and we'll go in depth next week. Just to conclude, I can write this information here, which reflect exactly this picture here. Now, instead of this form here, in this form. I don't know if I were to clarify why this form here is equivalent to this one. It's clear, no? I can consider a vector on the left part, consists of y1, y2, ym, which I called y capitalized and a vector I told you before. Circa remains because, as I told you, assuming that the best solution is not to meet everything. I will clarify next week why. But I told you also today. This expression here can be written in the matrix form if you do row multiply column. Row multiply column. I don't know if it's visible. This multiply this, A0 multiply x1 n. It's here. Plus, remember the rule, the rule, row multiply column. This multiply A1. And we have this. Until 1 multiply AN. If I do for all row, you can understand that this expression is equivalent to this one. Advantages of this expression, I will conclude. First of all, we have a matrix and vector, which can be eventually used in the computer. But the big advantage is, as I told you, we have a measurement vectors here. We have here a matrix, which consists basically of my X is the matrix, is written here, is an exploration matrix, because X was our exploration variable. Of course, here is the matrix is structured with respect to the model which I have, and is the polynomial with order n in general. N must be calculated. What is the best n? We will see in the next. But we can see that allows in this particular choice as polynomial to split definitively what I know. This I know because I measure. What I know because I explore with X, and what I don't know. Very important. With this particular choice, polynomial function, I can, if I know n, of course, if I know n, if n is unknown, I cannot split what I know with what I don't know, because here inside we have a something which I know, x1, x2, xn, but what I don't know. N I fixed is n, and the value. We will see how we can choose n. In this sense, if I can split what I know with respect to what I don't know, we are speaking about convex problem. We have seen in math, in gymnasium. On the left part, we have everything which I don't know, and the right, what I know. If I am able to obtain this, we have a solution. Not always, but we can try at least, numerically eventually, no? But until the polynomial second order, we can have a solution directly from the coefficients. Otherwise, we have to proceed numerically. To conclude, and then for today, we will see next week more in depth about the cost function. We can see here the possible choice of the cost function, which cannot obtain a solution exactly the sum. I think I have to explain a little bit better next week of the error here. I mean, it seems to be if the error here is the distance between the vector of the measurements and the approximating element on the curve, we will see that the problem at difficulty to find the solution, or the solution is 0. I meet all points, but if I meet all points, I assumed that the measurement speak the truth. And this is not always a good assumption, because the measurement is affected by noise. The statistical errors are always present in the measurements. This means if I meet all, I am assuming that what I am measuring is the truth. These are also different drawbacks, not only this one. The problem is, I conclude, look at this picture here. if I think that this is the best solution, I am assuming that these 2 points speak the truth. But nobody can say that another point lies on this line. Yes, of course, to say that is the best solution of this one is a little bit strange because with 2 points we cannot say much. We cannot say much. It could be that the third point is not exactly on the line, but almost on the line. Therefore, typically, and we conclude with this matrix here is a large number of row, large measurement in order to get information of the physics of the system, of the behavior of the system. Okay, just in time. Yeah, thank you for the lecture of today. We will see next week. I hope a little bit earlier, 15 past 8, so we can conclude at the right time. Thank you for attending the classes. If I have a question, I am here for you. I am here. Thank you.